We are surrounded by mysterious worlds. Worlds hidden from us by their sizes, too small or too large to be noticed. But now, it's possible to see these worlds. What's changed our perceptions? Technology, extending our natural senses, taking us on a remarkable journey from our own world through strange parallel worlds, down to the smallest and up to the largest elements of creation. Albert Einstein said, "It is entirely possible that behind the perception of our senses, worlds are hidden of which we are unaware." We experience the world around us through our five senses, but the one we rely on most is sight. For centuries, it was the artist who recorded and interpreted what we could see. St. Stephen's Cathedral in Vienna was started 850 years ago. In the 12th century, artists could only perceive a very limited world, with humanity at its center. But since then, science has expanded those horizons, looking outward beyond our planet and inward to the micro-worlds beneath our feet. The first microscopes revealed worlds we never dreamed existed. And electron microscopes can take us further into even smaller worlds. The atomic force microscope can show us the bizarre world of molecules, and even take us to a place where common sense is stood on its head, the unimaginable world of atoms themselves. And looking outwards, telescopes in space take us beyond our solar system, beyond even our galaxy, to the furthest regions of our universe. And humanity? We exist right in the middle of all this wonder. We're exactly halfway on the journey between atom and universe. In the past, artistic imagination challenged and probed the limits of our perceptions. But now, scientific imagination paints an even larger picture. Science has given us the tools to see our lives in a truly vast perspective, as just one layer amongst the many that make up our universe. And the first step on our journey through these layers needs just a simple tool, a lens, bending light to magnify images. In the 17th century, a few simple lenses in combination made a microscope and revealed a world that we'd never seen before. We found out that a whole world could exist in a single drop of water. A water bear with legs and claws like a tiny bear. The first naturalists who saw these images often looked for parallels with their familiar, larger world. But for 400 years, this was the limit of our journey into the micro world. It wasn't until the 1930s that the next step was possible. All eyes work on the same principle as those first microscopes, by bending and focusing light rays. Some birds see much finer detail than humans, and microscopes do better than both. But in the end, there is an absolute limit as to how much an image can be magnified with light. To travel further into the micro world, we need a microscope that can see the world in a way that's never evolved in nature. At the turn of the 20th century, technology was finally advanced enough to do that. A microscope that sees the world not by focusing beams of light, but by focusing beams of electrons. Electron microscopes reveal exquisite detail, even in everyday objects. We may be unaware of these tiny worlds, but they're all linked to each other and to our own world. Everyday events in our world can create spectacular effects in theirs. A rainstorm just makes us wet. Very inconvenient for us. Yet on a bronze statue, the continual wetting and drying out over the years creates a familiar green coating, the patina. But this thin green smear is really a spectacular landscape. A landscape made up of crystals less than 1/100th of a millimeter across. Watching 10 years of weathering unfolding in a matter of seconds, producing intricate, tiny flower gardens of crystal. These crystal gardens are dead, inanimate. But this scale also hides a living world. A patch of moss looks like a forest, and like any forest, it hides all kinds of strange creatures. These are tiny centipedes, only a millimeter or so long. And a pseudoscorpion, a minute replica of a scorpion. But at the next level, 10 times smaller again, the most numerous creatures are mites. Thousands of different kinds, millions of individuals. Many mites live on dirt and fungi, but this is a complete miniature world. Down here, as in our own world, there are both hunters and hunted. And the hunters here are fearsome. Armed with such powerful jaws, they can prey on mites their own size. With predators like this stalking the moss, some mites use camouflage. This mite has hairs on its back and attaches all sorts of junk to them, making it look like any other piece of dirt. Other mites use armor plating. Turtle mites can draw their legs up right inside their shell. It seems there's no end to the variety of different mites, all living their lives unseen until technology revealed their hidden world. But smaller again, the surface of a dead leaf is yet another world, covered in tiny bacteria. Exploring these tiny worlds doesn't just reveal unseen natural worlds. It shows us the way our own familiar world is built up, layer upon layer. A cathedral is actually made of small building blocks. Hundreds of thousands of individual pieces of shaped stone. A human body is also made of smaller blocks, cells. But to build a human body takes more than 30 trillion cells, creating a structure so elaborate that every individual is unique. No other person has this pattern of cells making a fingerprint. Different kinds of cells build different kinds of architecture to do different jobs. The lining of the gut is folded into elaborate structures to speed up the absorption of food. Or the surface of the tongue, covered in papillae that hide the taste buds. So, a human body, like a cathedral, is made up of building blocks. But unlike the cathedral's stone blocks, living cells aren't simple structures. They're miniature worlds in themselves. And in the same way the cathedral is more than the sum of its blocks of stone, a human body is much more than the sum of its 30 trillion cells. Until the 1940s, we could only make out the vague outlines of cells, so we thought they were simply bags of chemicals. But now we can see inside individual cells. These are images of incredibly thin slices through a single cell, and clearly they're far more than just bags of chemicals. They have their own elaborate structure. By adding together information from images like these, we can use a computer to recreate the inside of a single living cell. This is what it's like to swim through the inside of a living cell, and there are a few surprises in here. Scattered throughout the cell are sausage-like structures, mitochondria, the power generators of the cell. But mitochondria were originally free-living bacteria that became partners in ancient cells, and now we can't live without them. But over an individual's lifetime, cells are continually dying and being created. Over about 7 years, all the cells in our bodies are replaced. So if none of our cells are the ones we were born with, how do we stay the same individual? How do we know who we are? The answer lies at the heart of every cell, inside the nucleus. This is the next step of our journey into the world of molecules. Seen by an atomic force microscope, these are human chromosomes, each one made up from a tightly wound, folded molecule. And this is that molecule, DNA unraveled. The ridges are the very molecule that carries the code for life, and each bump on the ridge is an individual letter in the code. At this scale, it would take 23 days to travel along the entire code book. Every animal or plant has its own code written in DNA, a remarkable molecule creating all the diversity of life we see around us. The DNA molecule is so remarkable, it's even capable of creating a creature that can build a cathedral. But molecules are not the final limit. There are other levels beyond the structure of DNA for us to see. A pencil line is made of carbon, the same element that makes coal, diamonds, and most of the human body. It's even more of a fundamental building block of life than DNA. And these are carbon atoms, seen with an atomic force microscope, arrayed in a precise grid. Each atom a mere 10/millionth of a millimeter across. For 100 years, we thought atoms were the simplest building blocks of matter. But in the 1920s, even the atom was teased apart to reveal yet other layers. Atoms are made of orbiting electrons, and at the center, a tiny nucleus. But the world inside an atom is a very strange one. For something that's the building block of everything we see, there isn't much to them. If the outer shell of electrons were represented by this cathedral, how big would the nucleus at the center be? At this scale, it's so small, it's the size of this crotchet on the hymn book. So in reality, matter, stuff, is mostly empty space. What feels like solid matter to us is just the interaction between electrons. But deep in the heart of an atom, even the tiny nucleus can be split. And when it is, huge, unthinkable amounts of energy are released. The energy that fuels an atomic bomb. At these levels, we're beyond the limits of what technology can measure, a threshold below which we can't theoretically measure anything at all. But the scientific imagination can still probe even smaller levels, using the framework of mathematics. And imagination and maths have come up with a remarkable concept of the final building blocks of the universe: superstrings. These entities are tiny strings of energy that vibrate like the strings of a guitar. And as guitar strings produce different notes as they vibrate at different frequencies, so superstrings, vibrating at different frequencies, can create different particles, like electrons or protons. But the superstring is as small in relation to the nucleus as a single atom is to our solar system. Something so small might lie forever beyond the limits of our perception. So all we can perceive is the music of superstrings. The journey inwards has taken us to the limit of our perceptions and our common sense. But what happens when we look outwards? What does the world look like at larger scales than our familiar viewpoint? For example, to our normal senses, when walking through a forest, we see a collection of trees. Yet we can look down on it and see the whole forest from above. And from here, it looks like a solid green entity covering the landscape. In a way, that's also a true perception. The forest is like one organism. It's linked together at the microscopic level. The roots of the trees are all connected by tiny fungal threads weaving through the soil. Even in the largest forests, a microscopic web of living matter connects all the elements together. But we can see the woodland from an even broader perspective. From a satellite, we can watch the whole forest change color as autumn sweeps across the woodland. Satellites capture images of vast swirls in the atmosphere. We can watch the climate as it changes. Or see the vortex patterns of clouds created by islands. Using a different sense, infrared, we can distinguish between different types of vegetation, even the different crops grown by farmers. Satellites give us a completely different view of the Earth. Technology does far more than generate stunning images. It gives us more and more accurate measurements, even of something as complex as the climate. So does this mean we can use this information to make predictions? Can we forecast the weather accurately? The answer is no. There's a fundamental property of the universe that stops us: chaos. There are systems so incredibly sensitive to how they start off that the slightest change, even one too small to measure, can change the whole outcome. The weather is one of these systems. It's as if the air currents created by a butterfly's wings are enough to affect how the weather develops halfway around the world. Phenomena that are chaotic do follow simple mathematical laws. They just seem to behave in a random way. Chaos theory goes against common sense, and it does go against 500 years of scientific thinking. There are things that appear to behave randomly because of what they are rather than because of any outside effect. Ultimately, that means that we'll never be able to predict the weather. Chaos is everywhere. Even if we could predict the weather, we could never predict the path of each raindrop, or its path as it joins a running stream. Chaos has changed the way we think about the world. But seeing the Earth from even larger scales has given us yet more surprising insights. The Apollo missions gave us a completely new view of our planet. As Apollo 11 sped towards the moon, millions of people all across the planet saw images of the Earth as a tiny blue sphere, vulnerable and isolated, hanging in space. And it's the only world we know that supports life. And some people suggest that the Earth itself behaves like a living creature, regulating the climate to keep conditions just right for life. According to this Gaia hypothesis, it's the smallest creatures that are the most important. A green stain in the ocean is made up from uncountable numbers of tiny plankton. These are coccolithophores, each only a fraction of a millimeter across, but they exist in such numbers they can affect the climate. If, for example, the Earth warms up, the plankton breed faster, increasing their numbers even more. But they release a substance called DMS, which finds its way into the atmosphere. And DMS causes water to condense into droplets, making clouds. So more plankton means more clouds. And as white clouds reflect sunlight back into space, the planet cools down. The Earth stays in the narrow temperature range where water exists as a liquid, a vital condition for life itself. But our planet is part of a bigger system based around the sun, and sunlight is the other crucial ingredient for life. All the patterns and layers of life that we saw on the journey through the microworlds depend on sunlight to fuel their diversity. 500 years ago, we thought we knew that the Earth was the center of the universe. But now we understand that it orbits the Sun, and the Sun is at the center of the next level of reality, the solar system. The Sun is a fairly ordinary star, and it shines because at its center, hydrogen atoms are squeezed so tightly they fuse together, forming helium and giving off massive amounts of energy in the process. That energy, radiation traveling at the speed of light, takes about 8 minutes to reach the Earth. But the radiation has to get from the Sun's core, where it's created, to the surface, bouncing off the squeezed atoms as it does so. The atoms in the Sun are so tightly packed that a journey that should take 2 seconds in a straight line actually takes 10 million years. So the heat and light that fuel life on Earth today was created long before humanity even evolved. The Sun heats and lights the whole solar system, but just as important, it holds the whole system in place. Isaac Newton published his theory of gravity in 1687, and his calculations showed how gravity keeps the planets in their orbits. It seemed the universe was a place of mechanical precision, and using Newton's mathematics, the rising and setting of the Sun and the phases of the Moon could all be predicted. This same mathematics allowed us to calculate the path of space probes. In the past, all we could do was to point telescopes at the sky, but now we can send probes to visit the planets close up. Mercury is so near the Sun, it's rarely seen with the naked eye. In 1975, the Mariner probe showed us that Mercury is a dead, small world that rotates so slowly that its day is longer than its year. During its day, temperatures reach 350 degrees, hotter than an oven. And at night, more than 170 below zero. The next planet out from the Sun is Venus, the evening or morning star. But although it shines so brightly in the night sky, the planet itself is hidden by cloud. The Magellan probe used radar to see through the clouds and found a turbulent world. The greenhouse effect of the cloud cover keeps the surface at 450 degrees, hotter than Mercury, hot enough to melt lead. And then the third planet, home. At this scale, the Earth is unique. It's a double planet. Its moon was once part of the Earth itself, smashed off by an impact with a lump of rock the size of another planet. The next planet from the Sun is the stuff of science fiction, Mars. But the Mariner probes showed there were no Martians, no water, and little atmosphere. But the surface is spectacular, covered in deep gashes, including a Grand Canyon the length of the entire United States. There are also the remains of huge volcanoes, one rising 25 kilometers above the surface, the biggest volcano in the solar system. Perhaps the most famous probes are the Voyager spacecrafts, launched in 1977 towards Jupiter, the giant gas planet. Jupiter is so big it could swallow the rest of the planets with room to spare. It's a swirling, seething ball of gas, including methane and ammonia. Storms rage over its surface. Hurricanes far more powerful than any on Earth. Beyond Jupiter, Voyager journeyed on to another gas giant, Saturn, with its famous rings. The rings aren't solid. They're made of tiny fragments of ice and rock, possibly the remains of a shattered moon or comets. Beyond Saturn is Uranus, an ice giant. Uranus has a very strange movement. It rolls around the Sun on its side, its moons circling it like a giant Ferris wheel. So far out that the Sun is just a distant point of light. Neptune's orbit is so vast that a year on Neptune takes 165 Earth years, 2 human lifespans. Neptune is another ice giant like Uranus, but we know little more about it. But Newton's mathematics showed that between the orbits of Mars and Jupiter, there should be another planet. There isn't. Instead, there's a band of millions of lumps of rock, the asteroid belt. And in the year 2001, we even managed to land a probe on the asteroid Eros. We have no idea how many asteroids there are, but they range in size from small moons to house bricks. And at this level, the clockwork mathematics breaks down and chaos appears again. For the motion of the planets, Newton's laws are only approximations. Even the equations for just 3 bodies of similar size are hideously complicated beyond the reach of conventional mathematics. So it's completely impossible to predict what will happen in the asteroid belt. We've only just begun to realize how many asteroids there are and how close some of them come to Earth. Extending our limits of perception doesn't always make us feel comfortable. Meteorites, rocks from outer space, pieces of other worlds, captured behind glass for us to see. They've been wandering the solar system for millions, maybe billions of years. Some of them visit us from further than its outer edge. It took a major change in how we perceive the world to realize that the Sun is just another star, and our solar system is part of even bigger structures. To even think about the size of these structures, we had to invent a new way of measuring distance. A light second is the distance light travels in 1 second, about 300,000 kilometers. And distances within the solar system are measured in light minutes or light hours. Earth lies about 8 light minutes from the Sun. It takes light 43 minutes to reach Earth from Jupiter, so we're seeing it as it was 43 minutes ago. Saturn lies just over 1 light hour from Earth. But distances beyond the solar system are measured in light years, the distance light travels in 1 year. To find out what lies beyond the solar system, we sent a probe to look. The two Voyager spacecraft set off in the 1970s. Voyager 1 is now traveling at 96,000 kilometers an hour and is 11 light hours away, still transmitting signals back to Earth. It carries our signature on board, information about who we are and where we live, in case the probe meets other intelligent life. Voyager 1 has a new mission: to find the heliopause, the boundary where the solar wind, particles streaming out from the sun, are beaten back by the interstellar wind. It's heading for the edge of the solar system itself. But before it gets there, it has to pass through the Oort cloud, a motley collection of comets and rocks that it'll reach in 20,000 years. But it'll be traveling for 100,000 years before it meets the sun's nearest neighbor, Alpha Centauri, 4 light years away. Not one star, but a group of 3. As we look further and further into space, we're looking further and further back in time. Distant stars are so far away, their light takes thousands of years to reach us. We're seeing them in the past, at a time before human civilization existed. But beyond the stars is a bigger structure, the galaxy. The galaxy is thousands of light years across, a huge spiral structure of billions of stars. We live in one of the spiral arms, the Orion arm, about 2/3 of the way out from the center. From Earth, we see the disk of the galaxy edge on as the Milky Way across the sky. Scientists are only now coming to terms with the scale of the universe. But artists have always explored the infinite, the world beyond the one which meets our eyes, the hidden, the mysterious. As William Blake said, if the doors of perception were cleansed, everything would appear as it is, infinite. Worlds within worlds, worlds without end. Looking up at the stars takes us out of ourselves, gives us a sense of perspective. But there's a problem with looking up at the night sky. The atmosphere limits our view. The answer is to put a telescope as high in the atmosphere as possible, on top of a mountain. Mauna Kea in Hawaii, where the Gemini telescopes are so sophisticated that computers actually distort the mirrors to compensate for the atmosphere. They can stop the stars from twinkling and produce stunning views of space, clouds of dust and gas creating magnificent abstract images. But there's another solution. Put the telescope itself in space. The Hubble Space Telescope is gazing outwards towards the edge of the universe, seeing further than ever before and revealing layers of the universe we could never have imagined. The new generation of telescopes have shown how dynamic our galaxy is. We can watch the birth and death of stars themselves. When Hubble was turned to look towards the constellation of Orion, it could see deep inside the Eagle Nebula. It saw these massive towers of gas, star nurseries. In each of the pillars, gas is condensing and igniting nuclear fusion, and new stars are born. We can also witness the death of stars. As the star's hydrogen fuel runs out, it starts to fuse helium into other elements: calcium, potassium, and carbon. Eventually, no more reactions are possible, and the star dies, throwing the elements off in a spectacular cloud of gas. Our bodies are made up of these elements. We are, literally, stardust. But the biggest stars don't go quietly. They explode with unbelievable energy. A supernova. For a fleeting instant, a supernova outshines a whole galaxy of stars. In 1054, Chinese astronomers recorded a supernova as a star that shone so brightly they could see it in daylight. 1,000 years later, we see the leftover cloud of gas as the Crab Nebula, still expanding at thousands of kilometers a second. All this drama takes place within our own galaxy. But when Hubble was pointed at an empty patch of space and took an image with an exposure of 4 days, this is what we saw. Not black space, but more galaxies. Our galaxy is only one of billions. Galaxies come in different shapes: spiral, like our own, elliptical, or just irregular blobs. All the galaxies are racing apart from each other as the universe expands. But sometimes gravity wins out and galaxies collide. But galaxies are so vast and the stars within them so far apart that the galaxies just fuse together. It seems there's no end to the layers of structure within the universe. Galaxies themselves are part of bigger structures, clusters and superclusters. Our own galaxy is part of a small group of 6, which includes Andromeda and the Magellanic Clouds. But this group is racing towards the center of the Virgo supercluster, made up of more than 1,000 galaxies. The superclusters themselves are linked into one vast shape, the shape of the known universe. There might be more. But for now, everything we know is here. This is the outer limit of our perceptions. Is it the nearest we'll ever come to the Creator's view of the universe? And at the opposite end of the scale, will we ever find out what composed the music of the superstrings?